Greetings to everyone. I welcome you all to this series of lectures on applications of plasma in this course on plasma physics and its applications. So, I will be covering today in this lecture about a process called plasma nitriding. It is a surface modification technique, that means where we try to modify the surface. So, you will see that how actually a plasma is utilized in these processes to create the components with a better performance. So, why do we need to do surface engineering, right? So, surface engineering means where we are trying to engineer the surface property of a component to give better life and serviceability to the component. So, why is it essential? Because all the surfaces interact with the environment. So, environment can be a the aggressive acidic media, or maybe a high temperature or oxidizing atmosphere, or an electrochemical solution. For example, seawater which has a lot of salt content, and there the whatever the material we use in shipbuilding and all, that will be interacting with that atmosphere, right. So, there are some aspects which actually start from the surface, or basically they are only surface phenomena. These are like, suppose we look at the wear. Wear means how quickly a material removal happens in the event of a contact with another body. Body can be even an environment, it can be a fluid also. So, we want actually the components to have a low wear rate to be able to to sustain the components integrity for longer duration. And next comes is the corrosion or oxidation, right. So, where the electrochemically the material can leach out or something can deposit. So, there it is important that we have to engineer the surface to have a better resistance to these processes. And fatigue is a the means actually a cyclic loading. For example, if we take something, okay, and then if I keep on doing a cyclic loading, that means I pull it and leave it, pull it, leave it, then it is a cyclic loading. So, what we are doing is your surface is getting stretched and then compressed, maybe stretched and compressed. So, in this kind of processes, the components also fail much at a lower load. So, we also need to actually ensure that this fatigue resistance is higher. Of course, whenever any corrosion or rusting happens to the surfaces, aesthetics will also be the spoiled. So, that is also making the components life reduced. So, second thing is, why do we want to engineer, is that we want to improve two things: service life, that means the component should be useful for longer time, and functionality of components. For example, we have here I want to show this is let us say a gear, and this will be under this is where you have a continuous load being applied, right. That is where you are having a continuous load being applied. So, now during the process of it, for example, you have a drive, right. For example, our bike, or even bicycle, or anywhere, like you have a chain which is continuously running on it. That means these teeth are under constant wear and tear, right. So, now if the teeth are worn out, right, then automatically your load transfer will not be effective, right. Maybe your chain will be slipping sometimes, and then that there is a loss of energy in these additional processes. So, now if you look at it, the engineering the surfaces means we are working towards the environment sustainability. For example, we make this gear, okay. So, and now this gear, if we improve its lifetime, okay, that means we do not have to produce the large number of these parts in a particular year or so, right. That means because a one part is able to sustain longer time, that means whatever the energy which we spend in making these the components will be saved, right. So, that way actually we can actually contribute to the environment sustainability by doing a proper surface engineering to engineering components. So for example, some of the few applications I just gathered here, some of the applications where one can think of this kind of treatments are needed. These are all the the here is the fuel injectors in the engines where the fuel is injected into the engine. So there actually we want that the nozzle has to sustain a lot of wear, tear, and also the high temperature and also any chemical attack from the fuel. And then as I told you that the gears, see the gear teeth, for example, if you look at the gear teeth will be under constant load. So there we want that it has to be strong. And then the cutlery, suppose for example, if you see here, whenever you are using any of these the butter knife or the fork or the spoons, these are continuously used with the food what we eat, right? You are stirring something with a hot liquid and all that. So we don't want any leaching out of metallic ions into the food which can go into our body, that can create a lot of the harmful effects. So we need to reduce these things, and these are all the things where we can do the surface engineering. And in biomedical applications, the artificial knee implants and all. So when they are placed, actually the knees and all, when you see joints where actually the two surfaces are in their constant action, right? So there actually the surface needs to be strong. Okay, that is where we also see it. And the watch cases or even the mobile cases, right? The watch which is always on on our hand, where we are sweating and all, the sweat is actually the the salt solution, right? So then we don't want any corrosion to happen to the the back cover of your watch or the casing. So for example, there is one example is given here, a watch where this kind of surface treatments are done. And now heavy applications like the gun barrels, right? Gun barrels, you will have the lot of the your bullet will be fired and it will be passing through the gun barrel, right, in a particular path at a very high velocity. So it will be in the touching the surfaces, and these surfaces, if they are getting worn out with the time, right, your gun barrel dimensions have changed, I mean the internal dimensions, that will not give you the same efficacy as it was designed for if it is worn out. So here are some more examples like a crankshaft in automobile industries, right. So in automobiles, so these crankshafts are also the surface engineered. And for example, here you see a a turbine. Okay, so the turbine means, like for example, I'll give you, like we are talking about a hydro turbine where the water with a high pressure or a high potential is falling onto the blades of these turbine, and this water is not a filtered water, right. So you are having all the hydro turbine plants where the water is coming from the rivers and from the reservoir, and it is falling on it. It can have a slit, okay, some stone, some sand. So with all those things will be falling on these blades, right. So then these blade surfaces have to sustain wearing out of that. Okay, that is the case with a hydro turbine. But if you look at a steam turbine, right, where you are operating at a high temperature with a high pressure steam, right. Now at this high temperature, the blades have to sustain that high temperature, they should not sag down, and at the same time the oxidation, because you have a oxygen presence, and it should not actually oxidize severely and spall off, right. So those are the conditions which we can see. Then screws and nut sleeves, okay. So the especially when you look at the screws and nut sleeves, right. So when you have these threads on these nuts and all that, right, and you want to use it frequently, right, you tighten it and then sometimes you open it again for some repair and then you want to tighten it. So if these threads are not strong enough, okay, if you do it 2-3 times, then that it is gone, okay, all will become flat. So some biomedical applications here, what is shown is one dental implants for enhanced biocompatibility, which are also usually titanium alloys or stainless steels, okay, which also gets the surface engineered. And lot of surgical instruments, right. So the surgical instruments also need to have a surface which is very smooth and though no roughness. The reason being, surfaces being rough means it can capture lot of microbes and all that, right. So, the bacteria or viral things can sit on those crevices, so that the cleaning won't happen perfectly, right. So, that is where actually these kind of treatments are done to these surgical instruments too. So, now how this surface engineering is done, right. So, there are different ways one can do it. As you can see, either you can change the chemistry of the surface. Chemistry means you have made, let us say, that something with a titanium, and now your component you have made, but the surface chemistry you want to change it. It won't be titanium, but it can be maybe titanium plus something. Okay, so that kind of a surface engineering can be done. So, there actually you can do the change in the chemistry. Chemistry means the composition of the surface will be changed, or you can change the structure. Here the structure means the crystal structure. Let us say that that there can be material can exist, or elements or alloys can exist in different phases. Phases means usually they are distinguished based on a difference in the composition or the crystal structure. For example, if I have a iron FCC, then it will be relatively the easy to deform, right. If I have a iron BCC, it will be difficult to deform. So, I do not want to go into the details of it, but I would like to make you understand that the crystal structure gives also the specific property to the material. So, how can we change the chemistry of a surface? You have to diffuse in something, right. So, that is the one way. You have to provide some element which diffuses into these surface regions. That means only up to some depth this element will diffuse and changes the property there. Okay, that is the one way the chemistry of a surface region can be changed. And you can also do that the plastic deformation of the surface. That means you have a sample surface, you just hammer it, or you take a sand and then blast it with a sand, so that you create a lot of deformation on the surface. Because of the deformation, it becomes harder. Okay, it is called hardening by straining. Okay, it is called strain hardening. Okay. So, now to change the properties of the surfaces of components, you can do simply the thermal treatments. That means where the skin of the material can be heated up to some temperature and cooled at a certain rate to change the surface characteristics. Or you can do also the thermo-mechanical. That means you heat up and also deform the surface, okay, and then cool it in a particular way. It is called thermo-mechanical. The other variant is the thermo-chemical. That means you heat up the substance and bring it in contact with an atmosphere which is able to supply an element which you want to diffuse into the surfaces of the components. So, one thing you must realize that surface engineering comes as a last step usually in any component manufacturing. Suppose if somebody is making this gear, right. So, the surface engineering comes once he machines it and makes all the teeth, the everything by machining of the material, and then you do the surface engineering at the last, right. Why it is important? Why it is that means whatever the method you choose to make these gear teeth harder and can sustain for longer time, you have to do it in such a way that its dimensions are not changed by your finishing treatment. Suppose if I heat it up some temperature and cool it down and all, there will be thermal stresses, right. When we take anything, you heat up and suddenly put it in water, sometimes you see that part is cracking or it can bend also because of thermal stresses. Thermal stresses come because of differential cooling and heating of the material at different locations of the sample, right. So, that is why we need to make the component when it is soft, we like it, right. If I am given a material in a soft condition, I can easily cut it and make it into a shape, okay. And after that I want to make it harder. I want to make it harder only the surface, not everything, okay. Why we need to only harden the surface, not everything, is there are two properties I want to bring it here. One is called the toughness. Toughness means, for example, if I have a gear, sometimes it will receive shock loads. Shock loads means suddenly some accident has happened, okay, it will receive some impact. When such a thing happens, we don't want this to break into pieces, right? Rather, we like that it can deform a bit but still remain as a part, okay. So that is why we use always the metallic materials which have a toughness. For example, if somebody is constructing a building, in the pillars you use a steel reinforcement. Because why the steel reinforcement? Because the steel will not allow that building simply collapse. It will show that at least it is sagging down, it will give you a signal that yes, it needs to be repaired or something, so that the safety is the highest when you have a metallic structure. But now in this case, if I make the entire material of this gear very hard, yes, the surface property will be good, but when it receives any impact load, it will break into pieces, okay. That means it cannot absorb the energy, because energy absorption can happen if the energy can be utilized in changing the shape internally, right. So that is why these treatments are given at the last, and that means when I do the treatment, there should not be too much change in the dimensions, otherwise this won't fit into the application for which I have made it. Once I do surface engineering, I want to avoid doing any machining, because you only changed the surface, and if you want to machine it off, then you will lose whatever the the property change you introduce it there. So this is about the modifying the existing chemistry. Another way is coating the surface with another material, okay. We also hear about coatings, right. That means you simply deposit something else on it which can protect it from environment. The best example is all the mild steel grills and railings which we see, they are all painted, so that atmosphere interaction is minimized by having another material. And there are also the one can do the electroplating, right, in lot of places where the people use electroplating, or you can do also PVD or CVD kind of processes where you can deposit something else onto the existing the component. So we will be in this lecture I will be focusing on surface modification, okay. Surface modification is like you want to modify the existing surface chemistry. I don't want to deposit something as a separate layer on top of this material, okay. So how we can do this? Whenever you want to change the surface, you bring something else which you want to enter into this material and give the temperature, right. You make a junction, let us say I have a steel, I bring in let us say aluminum, I attach it and keep it at some temperature, then aluminum diffuses into my other material, okay, and then it leads to the property chain. So now which elements to diffuse in? We have agreed that we should not alter its dimensions, right. That means I should not heat it up to very high temperatures, okay. So the low temperatures are preferred. And now when I want to diffuse something into the material at low temperatures, then obvious choice would be small elements, okay, not the large elements. I cannot diffuse in tungsten into steel at low temperature, right. I need a very high temperature to make tungsten to diffuse into steel. But I can choose the elements like nitrogen, carbon, boron. These are all actually the small elements. That means their atomic radius is smaller in comparison to let us say the sizes of iron or nickel atoms, right. And they are so small, they can easily fit into the interstitial sites in the metallic lattices. For example, here you can see that these are all the elements, let us say a crystal structure is made up of these elements. For example, let us assume that these are iron atoms, and in between you have these regions, right. These are all called interstitial sites. That means these vacancies are already there, it is a vacant space. So if I have a small elements like nitrogen or carbon, and if I bring them, they can easily diffuse through these spaces available, okay. That means at a low temperature in a reasonable time, you will be able to diffuse in to a larger depth an element like nitrogen or carbon, okay. So and next thing is, what are the different processes available, right. So when we want to diffuse in the nitrogen into the component, there is a treatment called nitriding. Nitriding means you are diffusing into the metallic lattice and nitrogen atoms. Okay. And when you diffuse in the carbon atoms, it is called carburizing. Okay. And there is a process called nitrocarburizing, where you can diffuse in both carbon and nitrogen. Okay, the simultaneously both can diffuse. So it is called nitrocarburizing. Well, now let us say that when we take example of nitriding, then you need nitrogen, right, which needs to diffuse into the material. So what would be the obvious choice for nitriding? Nitrogen source in nature is highly sustainable source is only the molecular N2 gas, which is available plentifully in our atmosphere, right. We all know that 70% of our atmosphere contains nitrogen. So, but nitrogen is present as a N2 molecules, and these are very strongly bound. Okay. The binding energy between the nitrogen and nitrogen atom, which is a covalently bonded in a N2 molecule. And unfortunately, N2 molecule cannot fit into these interstitial voids available. Okay. It cannot fit in as a N2 molecule, is much bigger than the void size. A single nitrogen atom can fit in. So that implies that first I need to dissociate N2 molecule into nitrogen atoms. Then I can diffuse in the the nitrogen into the substrate. Unfortunately, considering that it is a strong binding energy between nitrogen atoms in N2 molecule, so we need to apply very high pressures and high temperatures, which are not practicable in reasonable sense. So then other way is that look for nitrogen source in which nitrogen is not very strongly bound. For example, ammonia, NH3 molecule, right, in which nitrogen is not very strongly bound, because NH3 is a very metastable compound. Okay, so it can easily dissociate into nitrogen and hydrogen. So that implies it can always release one nitrogen atom whenever NH3 dissociates, and that means if you use ammonia as a nitrogen source, we can pump in nitrogen. In the current context of this course, because we are talking about plasma applications, see, we can easily break the bonds of the compounds by using by creating a plasma, right, at a relatively low temperature. So that is possible by having a glow discharge. That means you feed in nitrogen gas and strike the plasma, right. That means you are actually dissociating the nitrogen molecules and then making them into neutrals or some ionic states, right. A mixture of that can be developed. So accordingly, we have different methods. One can say the gas nitriding, when you use a ammonia kind of a gas as a nitrogen source, or plasma nitriding when you use actually the nitrogen plasma, or salt bath nitriding. That means there are some salts like mostly cyanide or cyanate salts, where also nitrogen can be easily released for feeding into the materials. So what happens when you do nitriding of a steel? Okay. Now onwards, let us say that we will stick to the steel, because steels are largely used metallic materials. Okay. So where we make lot of components out of steels. So what exactly happens when we do the plasma nitriding of a steel? A schematic is shown here. This schematic is the cross section after treatment. For example, I do the nitriding for this material. That means I soak this material in a nitrogen containing atmosphere, it can be nitrogen plasma, then nitrogen diffuses in. Now I want to understand what has happened when the nitrogen diffuses. What you will do? You cut this and then you look at this way, you are looking at this cross section, so that this is the surface, and as I go down you can see what changes have happened. Such a schematic is shown here. Okay. So what happens when nitrogen, initially when you start the nitriding, nitrogen simply dissolves through the octahedral voids in BCC iron. Okay, I am considering a ferritic steel for example. That means crystal structure is now BCC of the matrix phase. And then this nitrogen can go in and it gives you the hardening, and when it is only dissolved, okay, the nitrogen is only dissolved, that means the iron atoms and chromium atoms and other atoms of the steel, they do not move, they remain as they are. Only nitrogen is going and sitting randomly in the available voids, okay, the interstitial sites. Then it is called diffusion zone, that means things have simply diffused, okay. And now you are diffusing in nitrogen, right. Let us say that you have some element in your steel which has a strong affinity to nitrogen, for example aluminum, okay, or titanium. Then the titanium and the nitrogen can come together and develop the titanium nitride particles, okay. So you can have actually the the particles of titanium nitrides, okay, can develop in the diffusion zone. Now these are very hard particles, they are very strong, these are nitrides, compounds, right, that give rise to increased hardness, and also it give rise to the improved fatigue endurance, okay. Fatigue endurance means, let us say that I take something, I am applying a cyclic load, right, I pull it by certain magnitude and leave it, pull it, leave it. Now up to some load it survives large number of cycles, it will not fail up to some load, okay. So up to that load it is called, that is the fatigue endurance limit, okay. Up to that load in a cyclic condition it can survive. So now once the nitrogen is coming in more and more, right, then you will develop a so called compound layer, okay. You can see here on the surface, that this is called a compound layer, that means here now nitrogen and the iron together they form a different structure, that means different crystal structure. It is no longer steel, it is a nitride, okay. So there are different nitrides, gamma prime and epsilon, okay. These nitrides are very hard, okay, and then they give rise to the lot of wear and corrosion resistance, okay. In summary, compound layer offers wear and corrosion resistance and the diffusion zone offers fatigue resistance, okay. So just to give an example here, what is shown here on this right side bar chart is that this is a particular stainless steel, okay. 316L means it is a grade name, you do not worry about it, it is a stainless steel, and people have studied what is the wear rate. Whenever we want to study the wear rate, for example I am rubbing two pieces, then how do you quantify the wear rate is actually the amount of material removed per unit time, right. So that is the kind of a wear rate you can offer. So that is plotted here on this y axis, wear rate, and this is actually without any nitriding, okay. This 800 is the wear rate, that is millimeter cube, the unit you can see here, for a unnitrided. Unnitrided means as stainless steel I made a gear and then how it is eroding. And then you see here there are different treatments are given. You see the drastically reduced wear rate here, okay. These are all the nitrided conditions, okay. So that is just to give you an example that one can drastically improve the wear resistance. So now I would like to summarize this lecture. So in this lecture what we have discussed is that what is the importance of modifying the surface properties of engineering components like gears, crankshafts or some biomedical implants or steam turbine materials. There are many actually, okay, wherever there is a wear and tear. And now we discussed about actually the the different ways one can modify the surfaces, what is the choice of elements one can choose, like elements like small elements like nitrogen or carbon are the best choice because we want to diffuse in at low temperatures. And then when these elements diffuse in, they will give rise to a hardening of the surfaces and even also forming a new compounds on the surfaces. So like for example it can form a compound layer or a diffusion zone when we do the nitriding, and then accordingly we can expect certain improvements in the properties. So with this now I would stop with this lecture, and in the next lecture we will basically look at more on the plasma nitriding aspects. Okay, thank you.